Memoization is an extremely useful technique for speeding up the running time of a program. Here's the simple idea. Just remember the results that have been computed before. So instead of recomputing things when you need their values again, you just keep them around. Here's another decorator. It's called memo. It takes in a function, which may take a while to compute. But we also keep a cache of the values that were returned by that function before. In the memoized version of f, we check and see first if the argument that was passed in is in the cache. If it's not in the cache, then we add it to the cache, meaning we make a mapping between the key, n, and the return value, f of n. Now we actually have to call f, which was originally passed in order to compute this return value. But once it's in the cache, we're never going to compute it again. Instead, we'll just return the return value that's already in the cache. Once I've returned the memoized version of this function, I will have automatic caching built in. So we keep a dictionary between keys and values, where the keys are arguments and the values are return values of f. And this memoized function has the same behavior as f, if f is a pure function. If it's a non-pure function, then we don't actually call f every time we call memoized, so it might have different behavior. So that's something to keep a lookout for. You can only really memoize pure functions and expect their behavior to stay the same. Let's see what happens when we use memo to speed up fib. So a memoized version of f keeps track of a cache, takes in an argument n. If n not in the cache, then we put it in the cache with the return value of f of n. We return what's in the cache every time, and we return memoized. Fib 30 used to take a while to compute. But what if we change fib to be a memoized version of fib? Then we can compute fib 30 rather quickly. In fact, we can compute fib 50 rather quickly, or fib 300, which is a very large number. But it's not that hard to compute. All we have to do is compute fib 298 and fib 299, which we do almost instantly with this memoized version of fib. So let's see if we can understand what's going on. I've restarted Python, so fib is slow again. What we're going to do is replace fib with the counted version of fib so we can see how many times it actually gets called. We'll give another name to that counted version of fib so we can access its attributes. Now, I'm going to change fib to a memoized counted version of fib. And we can even count that. And we'll call fib on 30, which completes instantly. There were 59 calls to the memoized version of fib, some of which reached the cache, and some of which actually called the underlying original fib function, which we called counted fib in this example, and its call count was 31. Now why 31? Well, there are 31 different arguments that we pass in. 30, 29, 28, all the way down to 0. And so that's exactly how many times we call the original function. Now what about 59? Well, let's take a look at what's going on. Here's our tree-structured recursive process, and we're going to keep track of actual calls to fib, times when we called the memoized version of fib and found the result in the cache, and times that we just skipped entirely. There must be lots of times that we skipped it entirely because we made so many fewer calls than we did before. So we call fib5, which calls fib3, which calls fib1, which returns 1. That's an actual call to the fib function. So is this call to fib0. But the next time fib1 is called, we just get the value that we've already computed from the cache. So this doesn't count as a call to the underlying fib function, but does count as a call to the memoized version. fib2 returns and then fib3 returns. The next thing that happens is that we call fib4, which calls fib2, which is already in the cache, which means we can skip over these calls to fib0 and fib1 entirely. They never even happen. And that's because this structure is something that's repeated from what we've already done before. So we find fib2 immediately, and when we call fib3, we find that result immediately as well, skipping these recursive calls. So with fib2 and fib3, we finally can return from fib4, and then return from fib5. So as you can see, for each value of n, fib is called exactly once, and for many values of n, the memoized version of fib is called a second time in order to finish the computation. But fib4 is never called a second time, and neither is fib5.